Now let us discuss the simplest quantum mechanical problem is a particle trapped in a box. This is a particle trapped in a box. So what we consider is this is a particle which is confined to a box of width L. This is the width L, and the particle assumed to move back and forth along a straight line between the walls of the box. So this is in quantum mechanics. This is solving this problem is one of the simplest quantum mechanic problem uh, to solve, that a particle is trapped. The particle is trapped in a box with infinitely hard walls. So quantum mechanically we can this this pictorial representation can be seen like this, that this is a square potential well with infinitely high barriers at the ends at x is equal to 0 and x is equal to 0 and x is equal to L. These are the walls of the box, and they are infinitely high. Okay, so anything inside this, if this particle is inside this, it doesn't have infinite amount of energy to come out from the box, and the walls of the balls, the walls of the potential well are so infinitely hard that the ball also cannot come out from the system. Not possible. So this is the problem. So quantum mechanically we will try to solve this problem with certain restrictions. You know, the restriction is that this is a square potential well with infinitely high barrier at the end of the end of the walls, and the wall of the box is infinitely hard that the ball cannot come from through the wall. So a particle because the wall of the box are very infinitely hard walls, so the particle does not lose energy when it collides with such walls, so that its total energy stays constant, and the potential U is, for convenience, is we know at potential at the walls, the potential which is my U is the potential is infinite at x is equal to 0 and x equal to L. That means at the walls, at the each ends. Okay, and inside potential is 0 inside the box, that is x greater than 0 and less than L. The potential is 0. Okay. The second thing, that the particle cannot have infinite amount of energy, so therefore it cannot exit outside the box, either crossing this wall or through crossing this wall. So its wave function psi is 0 outside the box. So we can write that the wave function psi, if I write the wave function psi, this has to be 0 for x less than 0 and x greater than equal to L. So psi is 0 means that the particle is not there when we're talking about particle is not at the wall as well as at this side greater than x, and also at the wall and at this side x greater than L. So the particle has to has inside the box. Okay, fine. So our task is to find that what is this psi? What is this psi? What is this wave function psi? What will be the form of this wave function psi within the box? Okay, that means 0xl, or at x is equal to 0 or x is equal to l. What will be the wave function form of this wave function inside the box? And then we will try to find the corresponding energy levels. So basically we will find the eigenfunctions, eigenvalues, energy levels, etc. Okay, so how to approach quantum mechanically to this problem, which is known as a particle in a box? So as you remember that we postulate a Schrodinger equation. Okay, so because this u is 0 inside the box, so we can safely consider the steady state form or time independent form of the Schrodinger equation, which we remember is d square dx square psi plus twice m by h cross square e minus u psi equal to 0. So but since u is 0 inside, u is 0 inside box, so we can write it as uh, d2 psi with dx square plus twice m h square e psi equal to 0. This is this we can write further as by d2 psi by dx square plus alpha square psi equal to 0, where I put this alpha as twice me under root by h square. So this equation is very simple differential equation of simple harmonic oscillator. You must have solved it, and the solution for this so is very straightforward. So solution, or say let's say the general solution for this, general solution for such kind of differential equation is can be written as psi equal to a some constant sine alpha x plus some constant b cos alpha x, where a and b are some arbitrary constants which we need to find out. Okay, so this is our general solution, psi equal to a sine alpha x plus b cos alpha x. Now we need to find the constant a and b in order to find out the wave function psi for the particle inside the box. So to find a and b, we need to apply the boundary conditions. Okay, so what are the boundary conditions? We need to apply the boundary conditions. So the boundary conditions are that psi is 0 at x is equal to 0, we will apply first, and then we will apply size also 0 at x is equal to L. Why is boundary condition? Because we are applying the condition on the wave function at the boundary, that is at x is equal to 0 and x is equal to L. Okay, fine, at these boundaries. So if we apply these boundary conditions, we can find out these arbitrary constants a and b. So remember that our psi is a sine alpha x plus b cos alpha x. If we apply the boundary condition that psi is 0 at x equal to 0, this implies that 0 equal to a sine, when we put x is equal to 0 here and here, this becomes sine 0 plus b sine 0, b cos 0, sorry. So cos 0 is 1 and sine 0 is 0. Okay, so this is 0 equal to 0 plus cos 0 is 1, so this is b. This implies that b is 0. Okay, so b is 0. Now the function, wave function psi, becomes a sine alpha x, because when b is 0, so this part is now 0. So now wave function is becomes sine a alpha x. Now apply the second boundary condition, which is, and this is psi equal to 0 at x equal to L. So what happens? We have uh, 0 equal to a sine alpha L. So now because a is a constant, a cannot be equal to, so we know that a cannot be equal to 0 because it is a constant. If sorry, a cannot be equal to 0 because if a is 0 and b is already 0, so the wave function, if b is already 0, b is already 0, and if a also becomes 0, then there will be no wave function, so it is not feasible. So for the feasible wave function, because the particle is there inside the box, there must be some wave function of that particle. We cannot put a equal to 0 in such case. So what can we do is we can put sine alpha L equal to 0. So if we put sine alpha L equal to 0, and this condition implies that alpha L has to be n pi, where n equal to 1, 2, 3 and so on. So when we put n equal to 1, this sign becomes sine pi, because sine pi, sine 2 pi, sine 3 pi and so on are all equal to or all 0. So now we have alpha L equal to n pi. We cannot put n equal to 0. You can see that we have started with n equal to 1. So the moment we put n equal to 0 here, so this become alpha L equal to 0. So for n equal to 0, alpha L becomes 0. So alpha cannot be equal to 0. That implies that L has to be 0. So if L is 0, then there is no box. No box. which is not the problem. So therefore we have started with n equal to 1, not with n equal to 0. Fine. Now since alpha L equal to n pi, since alpha L equal to n pi, and we know the value of alpha, this is twice m e divided by h cross square times L equal to n pi. Fine. Now we can write this as, if we solve this for value of e, so we can write en uh, equal to n square pi square h cross square divided by twice m L square, and for all n equal to 1, 2, 3 and so on. So this is important equation. We will discuss the consequence of this equation later on. So this is going to be our eigenvalue. These are going to be our eigenvalues. Okay, these are all eigenvalues. This is e1, e2, e3 and so on, whatever it is. Now let's try to find the wave function. Okay, let us try to find the wave function. Okay, so we can write now the wave function is like psi equal to a sine alpha x. Now we know that psi n we can write this is a sine twice m en, because alpha put the value of alpha, and this is h cross and this is x. If we put the value of en from here, so we get sine n as equal to a, let's put sine, this is twice m by h cross, put the value of en, this will be n pi h cross by twice m l, and then x. So all these will cancel out, h will cancel out, so psi n is basically a times sine n pi x by l for all n is equal to 1, 2, 3 and so on. So this is my eigenfunction, or the wave function. Corresponding to this, we have got eigenvalues, because you know this is, we write h psi n equal to e psi n. So if I apply Hamiltonian operator on psi n eigenfunction, we get the eigenvalues. Fine. So these are the wave function of the particle. It is inside the box, and these are the corresponding eigenvalues, that is the values corresponding to the energy levels of the particle inside the box. Now let us try to figure out that whether this wave function is well accepted wave function or not. Okay, so now you can see that uh, uh, this is psi n. Let's do like this psi n. Okay, this psi n, this psi n is like this psi is equal to a. Let's put sine uh, n by x by l for n equal to 1, 2, 3, and so on. So let's consider psi 1. So this will be a sine, put n equal to value 1, so this is pi x by l. Okay, this is a wave function for n equal to 1. So whether this is acceptable wave function or not. Acceptable wave function, if you remember, the wave function has to be continuous and single valued. So if I plot this wave function between x is equal to the two walls, which is this is x is equal to 0 and this is x is equal to l. So if I plot the wave function for n equal to 1, what I will get? So at x is equal to 0, if I put x is equal to 0, this becomes sine 0. So sine 0 is 0. The wave function is 0 at this. And if I put x is equal to l, so l will cancel out. We have sine pi. Sine pi is also 0. And what would the value of at x is equal to l by 2? So I put l by 2. So this will be psi 1 is a sine pi by 2 for x is equal to l by 2. And sine 90 degree is 1. Okay, it's a maximum. So this wave function will be like this. So the maximum at in the middle and 0 at the boundaries of the wall. So it's continuous. Similarly, uh, if you try to see the wave function for n is equal to 2, okay, like for psi 2, if you write psi 2, this will be a sine, this will be twice pi by l x. Okay, so what will happen? So let's try to plot it here. Okay, so this is the boundary n is equal to 2. Right, and this is x equal to 0 and x is equal to l. So what will happen? So at x equal to 0, at x is equal to 0, this will be 0, fine. And similarly at x is equal to 1, this becomes sine 2 pi. So sine 2 pi is also 0, so this is 0. What is at x is equal to l by 2? So when you put x is equal to l by 2, so this l will cancel out, so this is a sine twice pi l, and this x is l by 2, so this will cancel out, this will cancel out. This is sine pi, this is also 0. So here also the wave function is 0. So it will look like the wave function will look like this. So this is also for n is equal to 2, and this is for n equal to 1. So this is also a continuous wave function and single valued wave function. N is equal to 2, as n equal to 1, it is also continuous wave function and single valued wave function. So wave function, this wave function is like, if you try to see for every n values, it is continuous as well as a single valued. And if you try to find the differential of this, And the second condition was the derivative of the wave function has to be continuous as well as the single value. So if you find the derivative, this will also will be cos, so this will also be a continuous and single valued function. So it actually satisfy both the two condition of a well accepted wave function. What about the third condition, which is for normalization condition? That now let us take the third condition, which is for the normalization condition, and that we can write it like integral minus infinity to plus infinity, and this is psi n square dx. Let's calculate it, what it will be. So because uh, the length of the box is L, so the limit will be from 0 to x is equal to 0 to x is equal to L. So this is sine square dx, and we know the value of sine x, so this will be uh, 0 to L a square sine square, we have n pi x by L times dx. So using the condition that sine square theta is equal to 1 by 2 1 minus cos 2 theta, so we can write this as equal to 0 to L 1 by 2 we can take outside, a square also we can take outside, and then this will be 1 minus cos twice n pi x by L times dx. So this is a square by 2, and then we have 0 to L dx 0 to L, and cos of twice n pi x by L dx. So the further integration will give you a square by 2, and then dx, this is x minus L by twice n pi, and this will be cos becomes sine twice n pi x by L, and then putting the limit 0 to L. So if you put the limit of x equal to 0, so for x is equal to 0 this will be 0, sine 0 is 0, and for x is equal to L this sine becomes 2n pi, so this is also 0. So the only contribution will come from x, so this will be a square by 2, and if you put x is equal to 0 is 0, x is equal to L, so this will be L. Okay, so now what we have is minus infinity to plus infinity psi n square dx equal to a square by L by 2. So this is because a is a constant and L is also constant, so this integral is a finite value, so which is the condition of normalization, and so the wave function is normalized. So now we have to find so this implies psi n is normalized wave function. Now we have to find the value of a. What is a equal to? So this we can find by applying the normalization condition, that minus infinity to plus infinity psi n square dx uh, is equal to 1. So if we apply here in this equation, because this is equal to a square L by 2 and this is equal to 1, this implies that a is equal to 2 by L under root. So therefore the eigenfunction of the particle in a box is psi n equal to 2 by L under root sine n pi x by L for all n equal to 1, 2, 3 and so on. This is what we have the normalized eigenfunction. Okay, so now you can see that the normalized wave function uh, let me put it like this. Now, you can see that in this figure the wave function is plotted, this psi1, psi2 and psi3, and then corresponding probability density psi1 square, psi2 square, psi3, for this is for n equal to 1, n equal to 2 and n equal to 3. So we know that our psi n is basically given as 2 by L under root, and this is sine of n pi x by L for n equal to 1, 2, 3 and so on. So we have seen that this psi eigenfunction is normalized wave function, and this is basically acceptable wave function which is continuous single valued, and its derivative is continuous single valued, and is also normalized. And this represents the eigenfunction of the wave function of the particle inside the box of length L. So you can see for n is equal to 1, this is my wave function. For n is equal to 2, this is for n is equal to 3, this is. Similarly, if we try to find the probability density for this, so you can see these are the probability density for 3 levels, n equal to 1, n equal to 2 and n is equal to 3. So although this psi n in this figure may be negative as well as positive, but the psi square is never negative, it's always positive. Okay, and in a particular place in the box, the probability of the particle being present may be very different for different quantum numbers. What I mean to say that for a quantum number n is equal to 1, the probability of the finding particle inside the box is behaving like this. For n is equal to 2, behaving like this. For n is equal to 2, the behavior is this. For n is equal to 3, the behavior is this. So for different quantum numbers, the probability of finding the particle uh, inside the box is very different. For instance, if we take uh, n is equal to 1, so what it will be, I say for n is equal to 1, if I say psi for n equal to 1, for n is equal to 1, this psi 1 is 2 by L, this is constant, say this is sine pi x by L, and this mod psi 1 square will be 2 by L sine square pi x by L. Okay, so as this is very evident from psi 1, so this is the behavior is like this. Okay, behavior is like this, and if I try to plot the psi 1 square, so at x is equal to 0, at x is equal to 0 here, this is also 0 because sine 0 is 0, and for x is equal to L also here, this is 0, and for L is equal to 2, if I put L is equal to 2, uh, if we put x is equal to L by 2, so this becomes for x is equal to L by 2, in between here x equal to L by 2, so this psi 1 square is 2 by L sine square pi L, x is equal to L by 2, so this becomes pi by 2. Sine 90 is 1, so this is basically 2 by L. So this is value is 2 by L, which is maximum in the center, at the center of the box. And if you see for n is equal to 2, so at this position psi 2 square is 0, this particle is not there. So it's a very different behavior. For quantum number n is equal to 1, the probability of finding the particle is maximum in the center of the box, but for the quantum number 2, the probability is 0 in the center of the box. It is the probability is maximum at somewhere else. And in the same way for quantum number 3, the probability of finding the particle is maximum is somewhere else and 0 at those positions. So the behavior is and the probability density is different to different quantum number. This is what we get from the quantum mechanics. Classically, of course, suggests the same probability for the particle being there, but it could be anywhere inside the box. There is no such thing n is equal to 1, n equal to 2, n is equal to 3, and the maximum probabilities in the center or at the boundary, whatever it is. Classically, the probability is the particle is being anywhere in the box, but only quantum mechanically we can say that there is different possibility of finding the particle inside the box depending upon the quantum number. So that is why the energy is quantized and we have energy levels in case of subatomic particle when we consider such system in quantum mechanics. So this is the full picture of a particle in a box, how to deal with the simplest problem when a particle is trapped inside a box of infinitely hard walls, and that actually correspond to a particle trapped in an infinitely high potential well. So what we do, we postulate a differential equation, we solve it, and then we have the eigenfunction and eigenvalues, and we have checked that whether the eigenfunction is acceptable function or not, and then through the normalization we we, we try to figure out what is the actual eigenfunction of the particle which is trapped inside the box, and try to plot the wave function, which is eigenfunction, as well as the probability density. The next thing is remains is that about the energy eigenvalue, which is En, this is n square pi square, it's square upon twice m l square for n equal to 1, 2, 3, and so forth. This is the energy eigenvalue for a particle trapped inside a box. So the three main consequences, this is 1, 2, and 3, one can draw from this expression, that for every quantum number n1, n2, n3, we have corresponding energy E1, E2, E3, and so on. So pi is constant, h is constant, m is constant, l is constant, 2 is constant, only depending upon the quantum number n, which is the integer number. So the first interpretation is that a trapped particle cannot have any arbitrary energy like a free particle can. So this particle, which is trapped inside a box, cannot cannot have energy of any sort: 1 by 2, 3 by 2, 5 by 2, 7 by 2, 2, 3, 4, 5. It cannot have, like a free particle can have any sort of uh, arbitrary energy. But if the particle is trapped inside some potential, then it is going to have some discrete energy in terms of like E1, E2, E3, the multiple of integer multiple of H cross. So the fact of its confinement leads to restrictions on its wave function. Okay, so and that allow the particle to have only certain specific energy and no others, because we know that we write h psi n is equal to E psi n. Okay, so when the particle is trapped, then there is a restriction on this wave function. So the confinement leads to a restriction on its wave function, and because of that, the particle can only have a certain constant value of energy and no other energy, and that these energies are depending on the mass of the particle and on the details how it is trapped. Because what is the mass of the particle, and what is the size and structure of the system in which this particle is trapped. Pi, h, and 2, all other things are constants. So when the particle is trapped, there is a restriction that the particle can have only certain type of eigenfunction, and the corresponding to this eigenfunction, this can have only certain type of energy, and that depends upon the mass of the particle and the details how in which the particle is trapped. So the important thing is the energy is quantized. When the particle is trapped, it's not going to have any arbitrary energy value, it's only going to have a quantized energy, integral multiple of h. So the second interpretation is that a trapped particle cannot have zero energy because we're not starting with zero, we are starting with one. I have argued it for why we are not starting with n equal to zero. So when for n is equal to zero, E will be zero. It's not so there. So a trapped particle cannot have zero energy. Zero energy, when I say zero energy, that means the particle is stationary inside the box. But if the particle is stationary, that means if V is zero, that means the de Broglie wavelength, that is, which is lambda equal to h upon p, so you know h upon mv. So that becomes, the wavelength becomes infinity. So if the zero energy means the particle is stationary and speed is zero. So when the speed is zero, its de Broglie wavelength will be infinite. So but there is no way to reconcile an infinite wavelength with a trapped particle. So such a particle must have at least some kinetic energy. So the exclusion of E equal to zero for a trapped particle, like the limitation on E to a set of discrete value, it is a result with no counterpart in classical physics, where all non-negative energies, including zero, are allowed. So the second interpretation consequences of this eigenvalue is that the particle is not stationary. It is not going to have zero energy, because if it's so, then particle's wavelength, de Broglie wavelength, will become infinite, which is meaningless when something is trapped inside something, some dimension, and it is going to have an infinite wavelength. Fine. The third consequence is that, because if you see the expression of En, it's a Planck constant, which is 6.63 into 10 to the minus 30 joule second. This is very small quantity. The quantization of energy is conspicuous only when m and l are so also small. Okay, what does it mean? That when I say this, the energy is quantized when something is trapped, it it meaningful only when m, mass of the particle, as well as l, in which the particle is trapped, or the details in which the particle is trapped, is also very small, very small. Otherwise, what will happen in the numerator, we have h square, which is 10 to the minus 34 squared 10 to the minus 68. And if this, in the numerator we have large numbers, then this is not going to work out. Okay, so energy will be so small uh, that will not be feasible. Therefore, so when we talk about the energy quantization, which is integral multiple of the Planck constant, is only there when the particle which is trapped and the details of the system in which it is trapped is also small. This is why we are not aware of energy quantization in our own experience, daily own experience. Okay, uh, like we can just a minute, we can see uh, if you'll calculate uh, the permitted energy, if we calculate the permitted energy an electron of an electron in a box of 0.10 nanometer across dimension. So this is the dimension of order of atomic dimension. Okay, so mass of the electron, if you put the mass of the electron, which is 9.1 into 10 to the power minus 31 kilogram, and putting the value of L is 0.10 nanometer, is we can write it 10 to the power minus 10 meters, and the value of H and pi, if you calculate En, so this will come of the order of uh, around 40 n square electron volt, which is feasible. Okay, which is feasible. We see in electron volt of energy in a system. But if we try to find out the permitted energy uh, for a marble ball of 10 gram, which is trapped in a box 10 centimeter across. So if you calculate it, En in this case, it will comes out to be like of the order of 10 to the power minus 64 n square in joule. So the minimum energy the marble can have is, if n is equal to 1, this can have 10 to the power minus 6 joule, corresponding to n is equal to 1. So a marble ball with this kinetic energy is going to have a speed of the order of is going to have the speed of the order of 10 to the power minus 31 meter per second, and therefore cannot be experimentally distinguished from a stationary marble, whether marble is a stationary or moving. So, but when marble is a stationary, we know that the de Broglie wavelength is going to be infinite, which is unphysical. So as a reasonable speed a marble might have is, say, something 1/3 of the millisecond. Say it is having a speed of 1/3 of a 1/3 meter per 1/3 meter per second. So even this is and this correspond to the energy, possible energy for the level of n 10 to the power 30 factorial. So if you go to the quantum number, which is 10 to the power n is equal to 1 2 3 4, that is 10 to the power 30 factorial. So the energy levels are going to be very close. It's not separated like this. This is going to be very close if we reach to this such atomic number. So there also uh, it's very hard to determine whether a marble can take on only those energy or any energy whatever. So in an everyday experience quantum effects are imperceptible, which accounts for the success of Newtonian mechanics in this domain. But only in the atomic dimension or the nuclear dimension the quantum mechanics is feasible or perceptible and successful in explaining the many physical phenomena which we cannot explain on the basis of the classical mechanics.